I'm going to make you write some things down. There were three things that we needed in order for our function to be continuous. There were three things we needed in order for our function to be continuous. Allie, what was one? Allie F.
Okay. The limit on the right is the same as the limit on the left.
Okay, so the limit on the right is the same as the limit on the left. Okay? What's another stipulation, Trenton? So there was like three things that told you that like the rules for being continuous. She said the limit from the right and left need to be the same.
And also
Okay, and the third point you kind of squished in there. So we need a limit, we need a point, and the limit and the point need to be the same. Okay? Which you got to experience drawing graphs that were continuous versus not continuous. So let's go ahead and write down the official definition. Okay, so before you write down, okay, f of c is defined. We have a coordinate. The limit as x approaches c exists. The right and the left limits are the same. And then the big kicker, the limit is the same as the function value. Okay? Write it down. Don't worry about this down here. Just write to number 3. I cannot stress enough how important this definition is. And you knowing the 3 different parts. Anytime I ask you to verify something is continuous, I better see 3 things. I better see you checked what f of c is. I better see that you checked to make sure the limit existed. And then you tell me that the limit and the function value are the same. Sometimes I have people only check the limits and go from there, but make sure you also include the function value. Okay? Can anybody give me an example of a family of functions that would always be continuous, no matter what? Parabolas. And what family of functions does a parabola belong in? Let's see. And what family of functions do quadratics belong to?
Yes.
Like think broad spectrum here. We have parabolas. We have cubics, maybe some lines. Those are all called what kind of functions? Polynomials, okay? Polynomials are always going to be continuous. Rational functions. They can't be continuous. They are discontinuous wherever our denominator is 0. Okay? What are the 2 different things that could happen when our denominator is 0 of a rational function? Our denominator, if it's 0, 2 things could happen graphically. Oh, and what's one of them?
Sorry, I was writing down.
That's okay, I'll ask it again.
Yes.
In a rational function, if our denominator is 0, 2 different things could be happening on the graph. What's one of them?
There could be a hole.
There could be a hole. Okay. Or there could be a, what, Julia? Yes, because what's there? So if we have a rational function with our denominator being 0, Owen says there could be a hole or there could be something else. There could be a vertical asymptote, which is causing that break in the graph. Okay? So, if you have a polynomial, no matter what, you know it's continuous. If you have a rational function, you know that it's going to be discontinuous at anywhere where your denominator is 0. Because a whole, discontinuous, asymptote, really discontinuous. Okay? Basically, if you have to pick up your pencil anywhere to draw your graph, you have discontinuity, whether it be a hole, or a jump, or an asymptote. Okay. So I'm going to go through some pictures, and then we'll look at some piecewise functions, okay, and talk about how they would not be continuous, okay, and then we'll get into some of our algebra parts, okay. So polynomials, always continuous. Rational functions, never will be continuous, where your denominator is 0. Now there are some rational functions where the denominator doesn't equal 0, in which case they would be continuous everywhere, okay? But if we want to find the discontinuities, we need to concentrate on that denominator. So you don't have to write this down, just sit back and watch. So here are some examples of discontinuous functions. Here, our limit exists, but there's no function value, so we're discontinuous. We have a limit, that's great, but there's a hole, not continuous. Here, we have a function value, but our limits aren't the same. Our limit doesn't exist here at C, so we're not continuous. That looks like a break. Okay, here the limit exists and we have a function value, but they are not the same, so we're discontinuous. Okay, all three things have to match up in order for us to have a nice, smooth, continuous curve. Okay. Let's just look at these graphs. I don't think you need to draw these. Okay. So this is not a polynomial graph. It's y equals the sine of x. But we know what it looks like, right? It keeps going like this. Is there going to be any moment of discontinuity here? No, we have no holes. We have no breaks. So we could say that this guy is continuous from negative infinity to infinity. We could say that. Okay? Now, let's look at this semicircle. On the actual semicircle, do we have continuity? Yes. Now it starts and stops, so we would have to say that this is continuous from negative 2 to 2. Okay? Because that's the only part of the domain that we have. Okay? Now what about my third graph? Do you remember what graph that is? It's the greatest integer function. Okay, so that stair-step function. Very obvious. Is it continuous? It is not continuous. However, we could say that we have continuity from 0 to not including 1. Because we have continuity along that stair step. And we could say that we're continuous here from 1 to not including 2 because we have continuity along the stair step. But as an entire function, it is not continuous. Okay. All right. Please write down this piecewise function. Okay. We want to determine this A value. A is a constant. We want to determine A to where this piecewise function is continuous. So, our definition of continuity has 3 items. Number 1, f of c exists. So, first of all, which x value are we concerned about it not being continuous at? 2, because that's the break in the domain. We could have this happening, or we could have this happening. We need to figure out which one. Or we need to force it to be this case. So the first thing we're focused on is x equals 2. So for our definition of continuity, we want to make sure that f of 2 exists. Okay? And if I'm going to plug 2 in to my function to get an output, which piece would I pick? Piece 1 or piece 2? 1, because it includes 2. Okay? So f of 2 is a times 2 squared, so we're talking about 4a. Now we need to concentrate on the limit. Okay? We need to ensure that the limit as x approaches 2 from the left and the limit as x approaches 2 from the right are the same thing. Okay? So if we look at our left-hand limit, that's this top piece right here. Okay, x is less than or equal to 2. We're plugging 2, we're using direct substitution in the top piece. I know it kind of feels like we already did that, but we're looking at the limit as opposed to the function value. Okay. Now, for our right-hand limit, we're going to use direct substitution down here in the second piece. So x plus a. Okay. Well, the definition of continuity says we want our limit to exist. So what needs to be true about these two limits? They need to be the same. So we need 4a to equal 2 plus a. Which means a is what? Thank you. Okay. And since our limits we force to be the same, and our function value is the same as this left-hand limit, then we know that condition 3 is automatically upheld. And so we can say that a is 2/3. A time where we would have to make sure to go to that third spot is if the function value was separated from what the left and right-hand limits would be. So if you had like 3 different pieces you had to check. Okay. Questions about that before we move on to types of discontinuity? Okay. There are 2 types of discontinuity, and it kind of goes back to what our conversation was before about what can be happening in our rational functions. So we know that a hole is going to create discontinuity. We know an asymptote is going to create discontinuity. And we know some sort of break in our graph is going to create discontinuity. Okay? Well, there's some types of discontinuity that we could fix and some that we could not. So we have what's called removable and non-removable discontinuity. Okay? Removable discontinuity means we could rewrite the function in a way to make it continuous. I'll show you what I mean. But removable means we could rewrite the function in order to create continuity. once we get the definition written down, I'll go to a picture and show you what I mean. So if we think about a whole versus an asymptote, which picture would be the easiest to fix if we wanted to make it continuous? A whole or an asymptote?
A whole.
And what could we do with the whole?
Fill
Fill it in, right? So anytime we have a whole, that's going to be a removable discontinuity. Go ahead and write down, write down this function for me. Okay, so we could easily remove the discontinuity by filling in the hole. There's the equation. Here's the picture with the hole. How do I know that there's a hole without dropping it? Okay, we can factor, and what has to happen in order for me to know that there's a hole there? Okay, so we have factors that cancel out, and we know, hey, there's a hole. So if we take this rational function, x minus 1 times x plus 1, all over x minus 1. Since these factors cancel, I know that there's a hole at x equals 1. So first of all, I know from here I have discontinuity at 1 because it makes our denominator 0. But specifically, since our factors cancel, we know it is a removable discontinuity because it is a hole. Okay? So I'm going to ask you specifically to identify which type of discontinuity, and you need to be able to tell me, hey, it's removable because you know that there's a hole. Versus non-removable discontinuity. What do you think that's going to mean? Asymptote would be a type of example, but like we can't fix it. A non-removable discontinuity means we are stuck with discontinuity. There is nothing we can do to change the graph in order to help it out. So an asymptote or a break in the graph is going to be a non-removable discontinuity. Okay, so an example of a non-removable discontinuity, here's our function f of x equals 1 over x. Okay, we mentioned before, anything that makes our denominator 0 is going to be some sort of discontinuity. So here we know x equals 0 is where there's a discontinuity, but since there's no factors to cancel out, we know that this is an asymptote. Therefore, it has to be a non-removable discontinuity. Okay? So for the last 6 minutes of class, we are going to take 4 functions and determine if they're continuous or not. Can we do that together? I think we can. All right. Oh, there it is. So I'm going to cover this. F of x equals tangent of x. You're mumbling something. What are you mumbling? Okay, Max does not think it is continuous. Alex, why would Max think it's not continuous?
Because tangent, the graph was like, it breaks so much.
Okay, what's in between all these things you're trying to draw?
Asymptotes.
Okay, there's asymptotes. How do we determine where those asymptotes are?
Cosine zero.
Why are you saying cosine is 0?
Because it's sine over cosine, so then
Okay, so we can change this to a fraction, right? And we talked about, well, we have discontinuity anytime the denominator is 0. We can't divide by 0. So what's occurring, we have non-removable discontinuities. Oh, I do not like writing that word. At x equals, where's cosine 0? Say cosine of 0 equals 1. Well, where's the cosine equal to 0? Pi over 2, 3 pi over 2, and 5 pi over 2, and 7 pi over 2, right? All of those. So, we could write that as pi over 2 plus pi n. So, pi over 2 plus pi, plus pi, plus pi, plus pi. Pi over 2 minus pi, minus pi, minus pi, minus pi. Does that make sense? Function number 2. Celine, what do you think about 2x cubed minus x? And how do you know that? What type of, it's polynomial, and any polynomial is going to be continuous everywhere. Woo, polynomials. There was a time where you and polynomials maybe didn't get along as well because we made you do like all of this crazy stuff with them, like long division and synthetic division and finding zeros. But now in calculus, polynomials should be your best friend. And maybe you got along with them back then. I know I did, but I know some people it's not their favorite. Okay? All right, 2 more. Write this function down. Number 3. What would be a good first step? Okay. I think it would be a good idea if you have a rational function to factor if you can. If you can't, then just set the denominator equal to 0, but factor if you can. What can we do? The x's cancel, which tells us there is a hole. So we have removable discontinuity at x equals 0 because there's a hole. But then we have non-removable. It takes you longer to write these words than it does to figure it out. Discontinuity at x equals 1 because we have an asymptote. And don't mind me, I'm going to go ahead and abbreviate that word because I don't have enough space. But I need you to be able to tell the difference between removable and non-removable. Okay? What if our denominator didn't factor? How would we figure out where it's 0? Mm-hmm. Set it equal to 0, but if it didn't factor, how would we solve it? If it was quadratic, you could use the quadratic formula. Okay, I think we have until 40, right? Which is in like 45 seconds. So let's just talk through this one quick. If we were to determine if this is continuous, what would we need to check? Okay, our 3 steps. Function value, limit from the left and the right, and if they match, then we could say it's continuous. This one is continuous once you check that. So if you wanted to do the work and check to see, we would be good. Okay? But I am going to be picky. When I ask you for continuity, I need to see that you found f of c. I need to see that you calculated the left and right hand limit. And then you compared them. Okay? I want to see all of them. All right? Okay. Do your homework tonight. And we'll see you tomorrow. I'm ready.